Thank you for your attention. I will briefly introduce our work analyzing bug fix for automatic barcode classification published on JSS in 2020. These are the authors. As we know, fixing software bugs is an important task during software development. There are a large number of historical fixed bugs in various repositories. The following figure is an example of historical fixed bug and its corresponding dev source code. In the case of fixing a new bug, the developer usually first searches for similar bugs to find inspiration for a possible fix. However, many of these similar historical bugs use the repeated repair patterns. Therefore, developers often need to spend a lot of time reading the bug fixes to filter out the best solution. This greatly reduces the efficiency of bug fixing. So, with a better understanding, one can then plan the best course of action to minimize the future impact of bugs. In fact, many classification schemas such as ODC, CWE, etc. have been widely used to manage bugs in various software projects. Furthermore, we manually observed that bugs of a certain course type correspond to a certain AST level modifications in the bug fix. For example, one fix as an if statement and the if conditional expression here is a check for null or boundary values. The course type for the bug corresponding to this fix is ignoring the extreme conditions. Actually, in order to verify the existence of the observed correlation between bug causes and the AST level modifications in the bug fixes, we did a preliminary analysis. The details are introduced in the article. So, the aim of our work is first constructing a representation method for the bug fixes. Second, exploiting the corresponding relationship between bug causes and the bug fixes to automatically classify bugs into categories. To achieve this goal, we face the following challenges. First, it is difficult to mind the connection between fixing source code and the cause of bug. Second, it is difficult to model the bug fixes. In order to solve the above challenges, we did the following things. First, we manually investigated a set of real-world historical fixed bugs and manually labeled the cause type according to combined existing bug categorization criteria. Second, we designed a representation method for the bug fixes based on TBCNN. Third, we propose a supervised learning approach based on the representation of fixed trees that can automatically classify the bug causes of the historical fixed bugs. Finally, we evaluated our approach, and the results showed that the fixed tree is effective to classify historical fixed bugs into corresponding cause types. The general framework of our approach is illustrated in this figure. First, we need to preprocess the commits of historical bugs to extract the bug fixes. Then we construct the fixed trees for each extracted historical bugs. Second, we represent the fixed trees based on the encoding method of TBCNN. Finally, we use the classifier to automatically classify the bug fixes into corresponding bug cause category. Especially in the construction part, we propose to represent each bug fix in the form of a fixed tree based on the AST structure. Using the tree structure is to preserve the natural syntactic structure of the source code and to intuitively represent the fixed action to each node of the tree. Then we designed the representation part based on TPCN. This part includes 4 layers: coding, convolution, dynamic pooling, and output. Then it is the classification part. In this part, we used 3 classification techniques for bug cause classification. The statistics of the dataset are briefly illustrated here. During the 2-round manual labeling, we introduced the coherence kappa for the labeling results to measure the agreements between the participants. To evaluate the effectiveness of our approach, we are concerned about 3 research questions: the effectiveness of our approach, fixed tree representation, and our approach across projects. This is the result. The experimental results show that there does exist a relationship between the bug fix and the cause of bugs, and the representation model we propose can improve the accuracy of bug classification. In future work, we attempt to further prune or reform the fixed trees to reduce the scale of the training data and improve the efficiency of the model. In addition, we also plan to study how to use this the knowledge in the source code directly to assist in the bug localization and bug fixing. Thank you very much.
Okay, then we are back. Do you have any question for Zhen for her video? So if you don't have, I have a question. And so you use 3 classification techniques in your model. So SVM and Bayesian and CNN. You use 3 classification techniques for your model, right?
Yeah.
Yeah. So do you think which classification technique is the most efficient for the classification?
I'm sorry, I can't quite catch you.
So which classification technique is the most efficient for the bug cost classification?
Yeah, but we do the classification. We do that process manually. So it is a manually a manual process is not how can I say that? Maybe is not exactly correct.
Because the rest of your video, you show the table, the results of your experimentation.
Yeah.
Yeah. So how can I interpret that result? Interpret that table. So which one is better, or is it good enough for the bug cost classification?
Yeah, we collect it from the HE standard and the other and from ODC we combined the 2 classification schemas. So we focus on the source code on the course type. So maybe it is enough.
Okay, so it is enough for the practical uses. Because you're the micro P and micro R and micro F1 is relatively high.
Yeah.
Great. Yes, we have 5 seconds. Then I don't see any questions yet. Yeah, but this next session will start within 10